Imagine a plant spread out over 11 million square feet, where thousands of specialists work every single day to assemble an aircraft made up of more than 4 million parts. Here, in Toulouse, France, giants of the sky are born, from the legendary A380 to the cutting-edge A350. Parts for these aircraft come in from all over the globe. Wings from Britain, the fuselage from Germany, and engines from the United States. This is not just a plant. It is the heart of European aviation and a true marvel of engineering. And now we are going to take a look inside. The Airbus plant in Toulouse covers an area of over 11 million square feet. Now, that is an impressive size for any manufacturing complex, and especially so in the aviation industry. This plant produces not only the A380, but also other aircraft models from the company, like the A350. To produce these technological wonders, Airbus uses more than 2,000 workstations equipped with the very latest technology. This plant is the heart of Airbus aircraft production and a complex logistics hub, where every stage of aircraft manufacturing is its own form of art. The Airbus plant in Toulouse was actually founded way back in 1946 under the name Aerospatiale. Initially, it was a French company specializing in aviation manufacturing, and it laid the groundwork for the future Airbus plant. All the early stages of the plant's operation involved creating aircraft for both military and commercial needs. The Toulouse plant was strategically chosen for its location, which provided convenient access to transportation and logistics routes within France and across Europe. Originally, the plant focused on developing smaller aircraft, but over time, it expanded its capacity and implemented new technologies to produce large passenger aircraft. In 1970, the company Airbus Industry was established, a consortium that brought together 4 major European aviation companies: Aerospatiale from France, Deutsche Airbus from Germany, Construcciones Aeronauticas from Spain, and Air Italia from Italy. From that point on, the history of the Toulouse plant became closely linked with the development of the aviation industry in Europe. This is where the production process for Airbus aircraft began. Aircraft that would become significant competitors to giants like Boeing. Over the following decades, the Toulouse plant expanded multiple times as aircraft production really picked up speed. In the late 1980s and early 1990s, the plant became the main hub for producing aircraft like the Airbus A300, the first certified wide-body aircraft, and the A320, one of the most popular aircraft in the history of civil aviation. Over time, the Toulouse plant became the primary production center for models like the A330, the A340, and the A380, that huge double-decker aircraft that became a symbol of Airbus. In the 2000s, the Toulouse plant underwent major changes and modernization to handle the production of newer models, like the A350, which was introduced to the market in 2013. For this purpose, new assembly halls were built at the plant, including large facilities for assembly and testing, along with new automation systems to boost production efficiency and precision. Manufacturing the Airbus A380 is such a complex and detailed process that it requires innovative methods and technologies for its assembly. Just imagine, each aircraft produced at the plant consists of over 4 million individual parts. These parts are supplied from all around the world, from China to the United States. For example, the main fuselage components come from Germany, the wings from Great Britain, and the tail section from Spain. That is right, the Toulouse plant primarily handles the final assembly of the aircraft. This is standard practice for major aircraft manufacturers. Major engine manufacturers, like General Electric and Pratt & Whitney, supply the powerful jet engines for Airbus aircraft. Additionally, various aviation systems and components arrive from the United States. China is a key supplier of various metal parts, plastic components, and other materials for the aviation industry. Furthermore, Chinese companies provide certain aerodynamic parts. Other parts, including structural elements and fuselage details, are supplied by various European countries, such as Germany, Italy, Spain, and Great Britain. Well-known Canadian companies, like Bombardier, also supply components for different Airbus models, notably for the A220. After being manufactured, these parts are transported to the plant in Toulouse, where they are assembled into a single, complete unit. This often takes several weeks, and the large components are transported using specialized methods, like ships or air transport. The Airbus plant in Toulouse covers an area of 11 million square feet. It is one of the largest aviation manufacturing sites in the world. First, inside the plant's enormous assembly halls, the aircraft fuselage is put together. This is the main body of the aircraft, composed of several large segments that are delivered separately. Each fuselage segment is a major part of the structure, joined together with the others using cranes and specialized assembly machines. A crane lifts the parts, and they are carefully connected using special bolts and welding techniques. This is how the frame structure begins to take shape, although it is not yet in its final form. Once the main fuselage sections are assembled, the wings are brought into separate areas for installation. These wings are heavy, and their installation also involves the use of hydraulic cranes. When the wings are ready, they are attached to the main fuselage structure. Special attention is paid to this stage because the join between the fuselage and the wings is a critically important part that affects the aircraft's aerodynamics and safety. The installation of all the necessary systems, electrical, hydraulic, and avionics, also happens during this phase. Parts are integrated in special clean rooms to prevent any damage or contamination. This is a highly precise process, as all the elements, like cables, pipes, and computer systems, must be correctly positioned within a limited space. Robotic systems are often used at this stage for the precise placement of these elements. Once the aircraft structure is nearly complete and all internal systems are connected, it is time to install the engines. This is another critically important step, as the engines play a significant role in the aircraft's overall stability. Large hydraulic mechanisms and cranes are used to lift the heavy engines and precisely attach them to the aircraft structure. This also demands a high degree of precision and care. As soon as the aircraft is assembled and the engines are in place, it undergoes a series of tests and checks. On the ground, they conduct tests on the braking systems and check the aircraft's response to mechanical stresses. All these operations take place on enormous testing grounds, which allow for trials involving various loads and speeds. At the same time, the functionality of all the aircraft systems is verified. The testing area itself covers about 2 million square feet. After all the tests and adjustments are done, the aircraft moves on to the finishing stage, where it gets painted and the final details are added: window sealants, stripes, logos, and other design elements. Before the paint is applied, the aircraft is thoroughly cleaned to remove any contaminants, grease residues, or dust. Following this, the metal surface is treated to ensure better paint adhesion. An important step is the application of an anti-corrosion coating, which protects the aircraft body from oxidation and other harmful factors. This coating is applied using special sprays or spray guns to create a uniform protective layer. The aircraft is then painted in several layers. Most often, special polyurethane paints are used, which provide a durable, resistant coating. These are applied using rotary atomizers, which allow for even distribution of paint across the entire surface. The aircraft is placed inside a special painting hangar, sort of like a large enclosed area, where the necessary temperature and humidity levels are maintained to ensure proper paint adhesion to the surface and facilitate quick drying. After the base color is applied, a top coat is added, which provides extra protection against atmospheric elements and also gives the aircraft a glossy finish. This layer also adds resistance to ultraviolet rays, preventing the paint from fading in the sun. After painting, the aircraft are inspected for any defects. If any cracks or bubbles appear in the paint, they have to be corrected. In the final stage, airline logos or special liveries are applied to the aircraft. This might involve not just applying paint, but also installing special decals or applying a protective film to the surface. This process can take up to several weeks for a single aircraft, depending on the size and complexity of the livery. In total, painting a complete Airbus aircraft requires about 3,300 pounds of paint. The process of installing the cockpit is one of the most complex and precise operations. The aircraft cockpit, especially in models like the A350 or A380, contains hundreds of different sensors, control systems, displays, and other technical elements that must be precisely configured. Altogether, a cockpit can contain up to 5,000 different parts. Interestingly, the assembly of the cockpit takes place separately from the main aircraft body. This is done in special workshops where the cockpit is fully equipped before being transported for final integration into the aircraft. The entire cockpit installation process takes several days and demands the highest level of precision, because any malfunction in the control or navigation systems could lead to serious problems during the aircraft's operation. Another crucial aspect is the integration of avionics, which are the aircraft's electronic control systems. These systems allow pilots to monitor flight parameters, engine status, the situation in the sky, and perform other critically important functions. Installing the avionics takes anywhere from several days to several weeks, depending on the complexity and type of the aircraft. More than 10,000 people are involved in the aircraft assembly process, including engineers, technicians, testers, and other specialists. The production cost for a single A380 aircraft is around $445 million United States dollars, making this project one of the most expensive in the world of aviation. Just for the development of new technologies and the improvement of automation processes, Airbus spends millions of dollars every year. Did you know that your old air conditioner could poison the soil, wreck the ozone layer, and even cost you thousands of dollars in fines? Every single year, Americans throw out millions of air conditioners, and each one is a ticking time bomb of toxic chemicals, heavy metals, and dangerous gases. In this video, I'm going to show you how they actually get recycled. Freon, copper, mercury, nothing gets spared. And trust me, this affects all of us. So first things first, why should anyone bother recycling an air conditioner the right way? To answer that, let's break down what's actually inside one of these machines. Air conditioners contain refrigerants. These are chemicals that can do serious damage to the atmosphere. Older units use ones that destroy the ozone layer. Newer ones, they may not harm the ozone, but they still contribute to global warming. The internal boards and compressors are loaded with toxic stuff like lead, mercury, and cadmium. If you just dump an old AC in a landfill, all that junk can leak out into the ground and water. Now, compressors also contain valuable metals like copper, aluminum, and steel. Those can be reused, cutting down the need to mine more raw materials. But here's the kicker. If you try to tear one of these apart without the right safety measures, those toxic materials can leak out, fast. That's why so many countries, including the United States, have strict environmental laws banning improper disposal. And yeah, in some cases, those fines are no joke. In the United States, old air conditioner disposal is regulated on a federal level by the Environmental Protection Agency, plus individual state rules on top of that. Now, we've already touched on how long these machines usually last. So let's dive deeper. Window and portable units typically last from 8 to 10 years. Split systems? They give you a few more. And those big centralized setups, yeah, the ones we mentioned earlier, they'll run for about 15 to 20 years. Keeping filters clean, topping off refrigerants, and doing regular checkups can stretch that lifespan. But in hot areas where ACs run all summer long, they tend to wear out faster. Once your system hits the end of its life, it loses efficiency. Your power bill goes up and repairs become a money pit. That's why most people end up replacing them, which means more units headed for recycling. There are several ways to recycle air conditioners in the US. A bunch of utility companies run take-back programs for old ACs. Some even offer cash, anywhere from $25 to $100, just for handing your unit over. All you gotta do is apply, and a technician comes out to pick it up and handle it properly. Big chains like Best Buy, Home Depot, and Lowe's will take your old AC for recycling too. Some states have dedicated drop-off sites for electronic waste where you can bring in your unit for free or a small fee. In many cities, there are special bulky item collection days. And some towns offer curbside pickup of old appliances, sometimes even for free if you book ahead. Even charities like Habitat for Humanity Restore take working ACs to resell or use in community programs. And a lot of stores have trade-in deals, where you bring your old one in and get a discount on a new model. When we're talking about centralized systems though, you can't just yank one out yourself. You need to call a licensed tech. They'll recover the leftover refrigerant using special equipment, then ship the whole system off for proper disposal. In many states, improper disposal can mean fines, from $100 to $500 on average. But in some cases, it can climb into the thousands. Bottom line, either take your unit to a recycling facility or use one of those special programs. That's the smart move. Once the AC arrives at the facility, the first step is a professional teardown to safely remove hazardous materials and prep everything for recycling. Removing Freon is a whole process that needs special tools designed to safely extract it from the system. The technician hooks up a refrigerant recovery machine to the AC's tubing system. This device uses vacuum pumps and pressure gauges to control the flow. The system gets opened through service valves, giving access to the Freon lines. The vacuum pump slowly pulls the refrigerant out and transfers it into a sealed recovery cylinder. The tech keeps an eye on the gauges to monitor pressure and make sure every last drop is extracted. Depending on the unit size and how much refrigerant is inside, this process can take anywhere from a few minutes to half an hour. During this step, the workers are fully suited up because contact with refrigerants can be harmful. The equipment's built to prevent any leaks. Everything happens in a sealed environment. Once the Freon is removed, it's stored in that sealed tank and later handed off to certified hazardous waste recyclers. With the refrigerant safely gone, the unit moves on to the disassembly phase, which is crucial for proper recycling. The techs set up special workstations at the facility. Before disassembly starts, they review the paperwork and lay out a plan, so they know exactly which parts to pull and how to sort them. The AC gets broken down into its core parts: the outer casing, compressor, heat exchanger, fan, electronics, piping, and smaller components. A typical unit has around 20 to 30 different pieces. The compressor alone might weigh between 30 and 50 pounds. Radiators, anywhere from 20 to 40 pounds each. They use both hand tools and machines, like hydraulic lifts and electric grinders, to cut or unbolt the big metal parts. This step takes about 30 minutes to 2 hours per unit, depending on size and complexity. Once everything's apart, the pieces are sorted by material: metal, plastic, and electronics. Around 90% of the metal in an old AC can be recycled. Metal gets cleaned of paint and grease, then sent for smelting and reuse. Plastics go to specialized recycling plants. Electronics that contain dangerous stuff, like lead and cadmium, are sent to e-waste recycling centers. On average, just one unit can provide 5 to 15 pounds of recyclable metal. That's a big deal when it comes to saving raw resources. Many recycling centers handle tens of thousands of air conditioners every year. That keeps a massive amount of toxic waste out of landfills. After the unit's fully disassembled, the next key step is sorting and prepping the materials for reuse. This process helps maximize resource recovery and shrink the environmental impact. After the initial cleaning, materials are sorted by quality standards. Metals get split into categories: aluminum alloys, steel, and copper. For example, copper wiring is often separated because its market value sits around $4 to $5 per pound. Plastic waste is grouped by type. The bundles for recycling usually weigh between 5 and 20 pounds. Electronic components are sorted by type: motherboards, capacitors, batteries. So recyclers know which ones need special handling, especially those containing rare metals. After sorting, all materials are packed up for transport. Metal parts go into containers headed for smelters. A single container can hold anywhere from 500 to 1,000 pounds of metal. Plastic granules are bagged or boxed up, usually in 50 to 100 pound batches, ideal for manufacturing. Electronics are shipped to specialized facilities, where they get broken down even further. Thanks to this whole process, a single air conditioner can yield a surprising amount of reusable material. Recycling and disposing of A to C the right way also saves energy. Smelting recycled metal takes about 60% less energy than making new metal from raw ore. And today, some companies are already rolling out tech to automate disassembly and sorting, making the whole system more efficient and less dependent on human labor. Every single year, more than 200,000 hydrocycles are sold all around the globe. And the overall market for this type of equipment exceeds $2.5 billion United States of America dollars. But how does a piece of composite material turn into a genuine water monster that can accelerate up to 70 miles per hour? What makes the Japanese Yamaha factory the largest hydrocycle manufacturer in the entire world? From automated hull molding to the most advanced engines and on-water testing, today we are going to unveil every secret of their production. Fasten your seatbelts because we are heading into a realm of high speeds and groundbreaking innovations. The design of hydrocycles begins with conceptual ideas and essential requirements for technical specifications. The very first stage involves identifying the target audience and the purpose of the hydrocycle. It can be a recreational model, a sports or extreme hydrocycle, or even specialized versions for fishing or rescue operations. Designers and engineers must consider not only the visual appeal, but also factors such as maneuverability, stability, top speed, comfort, and water safety. They carefully think through each detail so that the final product meets the needs of both beginners and seasoned riders. According to Statista, the global hydrocycle market by the year 2027 will grow to over $2.5 billion United States of America dollars, with an annual growth rate of 8.3%. This impressive forecast shows just how much interest hydrocycles continue to generate in different parts of the world, especially as new technology makes them more efficient, eco-friendly, and fun to ride. One of the biggest markets for hydrocycles is the United States of America, where more than half of all hydrocycles worldwide are sold. This country remains a leader in water sports development, partly because of its numerous resorts, lakes, rivers, and coastlines, which make hydrocycles immensely popular among both local residents and tourists. Hydrocycles are also well liked in Australia and Japan, where water activities are an integral part of cultural traditions, and people love to explore different forms of aquatic adventure. During the development stage, important factors include the design of the hull, which must be light yet strong and resistant to mechanical damage. For this purpose, high-quality materials such as fiberglass, composites, and aluminum are used to achieve the required rigidity without adding too much weight to the hydrocycle. Another critical consideration is the choice of engine. Most hydrocycles use internal combustion engines, although a growing number of manufacturers are experimenting with electric models, which offer cleaner emissions and produce less noise. In modern hydrocycle design, special attention is paid to innovative technologies, including digital control systems, integration of the global positioning system, and sensors for monitoring the condition of the equipment and improving navigation. These features not only make the experience more convenient for the rider, but they also boost overall safety through automatic stability control systems or engine rotation alerts. All of this simplifies the hydrocycle piloting process and makes it safer, even for first-time enthusiasts. The United States of America holds over 50% of the global hydrocycle market. Another notable trend is the rising demand for electric hydrocycles. Although they currently occupy only a small share of the market, their environmental advantages could make them a key part of the hydrocycle industry's future, since they help reduce emissions and lower noise pollution levels on the water. An essential element of design involves creating an ergonomic layout that ensures comfort during lengthy rides or races. Seats must be comfortable and provide proper support for the rider's posture, while also featuring a non-slip surface that holds up in wet conditions. Additionally, hydrocycles are equipped with various features, such as extra storage compartments, waterproof pouches, and cooling systems that help the vehicle operate at high revolutions over long periods. Developing new models also requires numerous water tests to check how the hydrocycle performs in real conditions. This process helps identify any weaknesses in the design or technical parameters, which are then corrected before the start of mass production, guaranteeing that customers receive a high-quality product. The hydrocycle development process is extremely detailed and demands meticulous attention at every phase, from designing the hull to testing the final product. Engineers, designers, and manufacturing specialists must work in close collaboration to produce equipment that is not just powerful and fast, but also safe and comfortable for users. Hydrocycles need to be easy to maneuver on the water, while also having enough durability to withstand heavy loads, water pressure, salt, ultraviolet radiation, and other environmental factors. These stringent requirements mean that the choice of materials for different hydrocycle components must be carefully evaluated to balance weight, strength, and resistance to corrosive elements. First and foremost, a key element of any hydrocycle's construction is its hull. This is one of the main parts that must be strong enough to resist mechanical damage and, at the same time, provide optimal hydrodynamic characteristics. The most common materials for hull manufacturing include fiberglass, composite substances, and aluminum. Fiberglass is selected because it offers high strength at a low weight and is resistant to corrosion, making it ideal for use in aquatic environments. In addition, it can be molded easily, allowing engineers to create sleek, aerodynamic shapes for the hydrocycle hull. Composite materials, which include polymers reinforced with fibers such as carbon or Kevlar, are even more advanced, delivering greater strength while reducing weight. They also exhibit excellent resistance to ultraviolet exposure and chemical agents like salty water solutions. By combining these materials, manufacturers can cut down on hydrocycle weight while improving speed and maneuverability, which is especially beneficial for sports-oriented models. When it comes to internal components, such as fuel tanks and cooling systems, manufacturers often rely on stainless steel or specialized plastic blends. Stainless steel is a long-lasting material that resists corrosion, making it perfect for repeated contact with water and various liquids. Plastic blends, such as high-density polyethylene, are used due to their lightness, durability against chemical and mechanical impact, and ability to function effectively for extended periods in high humidity conditions. Another crucial consideration is the choice of materials for hydrocycle engines. Lightweight yet powerful substances are essential for achieving high revolutions without sacrificing endurance. Typically, engine components are made from metal alloys, including aluminum, titanium alloys, or magnesium. These materials have low density, which helps reduce engine weight, and they have excellent thermal conductivity, which is critical for efficient cooling and overall engine performance. One well-known hydrocycle manufacturing facility is located in Japan, operated by Yamaha Motor Company, which is widely recognized as one of the leading brands in the watercraft market. Situated in the city of Iwata in Shizuoka Prefecture, this factory produces not only hydrocycles, but also other types of water transport and their engines. The Yamaha Motor Factory spans approximately 250 acres, making it one of the largest facilities in the world dedicated to water equipment production, including hydrocycles. The site specializes in manufacturing a broad range of water transport products, including diverse hydrocycle models, boats, yachts, and other motorized water vehicles. Every year, this factory turns out thousands of products, including over 60,000 hydrocycles annually, which secures Yamaha a substantial market share in the water transport sector. Thanks to the factory's expansive premises, every stage of production, from assembly to testing and packaging, can be carried out efficiently and in one location. One of the main automated lines is responsible for forming hydrocycle hulls using materials such as fiberglass and composites. This line is equipped with robotic arms that precisely shape and join individual hull components, delivering the exact design contours and a smooth exterior finish. In addition, automated welding and painting systems are used to process metal parts, such as engines and their subsystems. The line features robotic welding machines that provide accurate, high-quality welds, as well as automated painting systems that evenly coat components and offer reliable protection against corrosion. This advanced technology helps ensure the product maintains a pristine appearance and robust structure over an extended service life. The assembly lines have a real-time quality control system, which automatically identifies defects at any stage of production. This includes visual inspections using cameras and scanners capable of detecting even the smallest flaws in parts, allowing the factory to preserve the highest possible product quality. A distinctive feature of this factory is its extensive automation in the packaging and shipping phases. Once hydrocycles have passed all quality checks, they move on to automated packaging lines, where robotized systems assemble boxes and secure the hydrocycles inside transport containers. This process enhances shipping safety and streamlines logistics, ensuring that the products are delivered to customers in excellent condition and on schedule. The Yamaha factory continuously adopts the latest technologies in water equipment production. For instance, they use three-dimensional printing to create prototypes of new models, enabling faster testing and refinement of their designs. Moreover, the facility employs pioneering materials that help reduce the weight of hydrocycles, increase their corrosion resistance, and extend their service life. They also make active use of intelligent production management systems, which optimize manufacturing processes, cut down on costs, and shorten the time needed to produce each unit. As a result, the factory can expedite hydrocycle manufacturing and boost output volume, illustrating Yamaha's commitment to continuous innovation and leadership in the fast-paced world of hydrocycle development. 850 horsepower. That is the power output of the hybrid Lamborghini Revuelto. This is almost like having the force of 2 average tanks. Whenever you see a Lamborghini on the road, it is impossible not to turn your head. This is a car that shouts success and style, and it does so very loudly, thanks to its V12 engine. A Lamborghini is not merely an automobile. It is a symbol of status, luxury, and wildly high speed. However, this car is not just beautiful. Its heart is a genuine masterpiece of engineering. Shall I tell you about the engine? Lamborghini is renowned for its naturally aspirated engines that roar like a wild beast. The brand's most famous motors are the legendary V10 and V12, which provide not only insane power, but also an incredible sound that sends chills down your spine. The V12 engine was already present in the first Lamborghini 350 GT from the year 1963, and it remains the company's signature to this day. The establishment of Lamborghini was not merely a business project, it was an act of revenge. In the small town of Sant'Agata Bolognese, under the blazing sun of Emilia-Romagna, a company was born that challenged none other than Ferrari. Ferruccio Lamborghini was a successful businessman who became wealthy through the production of tractors. He owned an entire collection of sports cars, but he had problems with the Ferrari 250 GT because its clutch often broke down. One day, Lamborghini decided to express his dissatisfaction directly to Enzo Ferrari. He proposed improving the cars, but he was met with this response: "Ferruccio, you are just a farmer. You should focus on tractors and stay out of sports cars." Those words were the point of no return. Lamborghini resolved to build his own supercar that would surpass Ferrari. He hired the best engineers, including Giotto Bizzarini, the person who had developed engines for Ferrari. The team created that same legendary engine that became the heart of the first Lamborghini 350 GT. Even then, the car showed that Lamborghini was not joking around. It was faster and more comfortable than Ferrari. The first car was a success, and the company began to grow rapidly. Within only a few years came the legendary Misura, then the Countach, the Diablo, the Murcielago, and the Aventador. And now, for 60 years, Lamborghini has continued to be a symbol of status, aggression, and an engine's ferocious roar. The main Lamborghini factory covers 1,743,752 square feet. That is nearly the size of 23 soccer fields. This place is a genuine temple of speed and engineering artistry. All the critical steps in creating supercars are concentrated here. Massive pavilions equipped with ultra-modern technology merge with the craftsmanship of hand assembly, which remains an unchanging tradition of the brand. The factory includes a materials laboratory where carbon fiber is tested, paint booths where each automobile receives a perfect finish, and the exclusive ad personam division that allows clients to customize their Lamborghinis down to the finest detail. Every vehicle undergoes strict quality tests before leaving this temple of speed, bound for owners all over the world. In the year 2023, Lamborghini set a production record for the entire history of the company. 8,405 brand new cars rolled off the factory line. Every contour of the body is designed not only for aerodynamics, but also for maximum visual impact. The low profile, the aggressive front end, the sharp edges, and the massive air intakes all form the image of a wild predator ready to pounce. The signature guillotine doors on the Aventador or Revuelto models are an unforgettable sight. They lift upward. The moment you open them, you already look like a movie star. Buying a Lamborghini is not simply about money. It is about a way of life. Lamborghini owners want to stand out, be at the center of attention, and experience an adrenaline surge each time they press the gas pedal. It is no surprise that among these owners are soccer players, actors, business people, and even princes. Lamborghini has always been synonymous with exclusivity. Production is limited. Most models are released in small batches, and some appear in limited runs of 10 or 20 units. For example, the Lamborghini Centenario was produced in only 40 units, 20 coupes, and 20 roadsters. Lamborghini uses only premium materials, most of which come from the world's top suppliers. The main material is carbon fiber. Did you assume the body was made of metal? It is not. Carbon fiber is an ultra-strong yet lightweight material made up of extremely thin strands of carbon, each roughly 10 times thinner than a human hair. It is stronger than steel, but weighs several times less, making it ideal for supercars. Carbon fiber begins with polyacrylonitrile threads, which are a synthetic material similar to plastic. The fibers are heated in special furnaces with oxygen, which alters their chemical structure and makes them thermally stable. Then the fibers move into furnaces without oxygen, for instance in a nitrogen atmosphere. Under extreme temperature, they lose all inorganic components and are left as nearly pure carbon. These carbon threads are then treated to bond more effectively with polymer resins. The finished fibers are woven into fabric or laid out as ribbons. The carbon fabric is infused with resin and then shaped as needed. Lamborghini uses forged composites technology, where the fibers are arranged randomly, resulting in parts that are even lighter and stronger. The form goes into a high-temperature, high-pressure autoclave, where the composite hardens and gains extraordinary rigidity. Imagine strands thinner than a hair passing through furnaces at 3,632 degrees Fahrenheit. What comes out is a black thread that is 5 times stronger than steel, yet 7 times lighter. Instead of a conventional steel component weighing 33 pounds, Lamborghini gets a carbon substitute that weighs 6 pounds, while preserving the same strength. This material enables Lamborghini to craft bodies that are light, strong, and fast, reducing the vehicle's overall mass and boosting its aerodynamics and performance. Aluminum is sourced in Europe, especially from Italy and Germany. It is utilized for fabricating the chassis, the load-bearing body components, and various structural parts, since it is both light and strong. Suppliers deliver aluminum as sheets, profiles, or ingots. When it arrives as ingots, it is melted down and cast into blanks. Aluminum is melted in special furnaces at around 2,232 degrees Fahrenheit. The molten metal is poured into molds under high pressure. The casting solidifies in a matter of seconds and is then removed. The cast pieces are ground, excess material is trimmed off, and they undergo heat treatment to enhance their strength. Using aluminum makes the frame about 40% lighter than a steel alternative. Lamborghini's press machines can produce up to about 11,000 short tons of forming pressure. A single aluminum Aventador frame weighs a mere 504 pounds, which is essential for high speeds and maneuverability. Natural Italian leather arrives from renowned tanneries in Tuscany and Piedmont. Alcantara is sourced from a factory in Umbria for the upholstery. Carbon inserts are produced directly at Lamborghini. It may require 7 or even 8 cowhides to upholster the interior of one Lamborghini. Buyers can choose any color of leather via the Ad Personam personalization program. Lamborghini uses premium Napa leather and aniline leather, which both have a natural texture and softness. All leather sections are handcrafted to maintain exclusivity. The leather is manually cut for each part to avoid defects or unevenness. Every seam is also stitched by hand, ensuring precise quality control. Special leather threads are used for this purpose. Each piece is dyed and treated to achieve the requested appearance and texture, consistent with the client's wishes. Once every piece is ready, it is assembled and installed in the automobile. Alcantara is a high-end synthetic material that resembles suede in both look and feel. It is widely applied in the automotive sector. Alcantara is soft, matte, and holds up better to wear than genuine leather. It is also twice as light as leather, which is critical for supercars. It does not fade, retaining its color even under direct sunlight, and it is made of 68% recycled materials. The assembly process begins with preparing the vehicle body and chassis. This involves installing a foundation constructed from lightweight metals or carbon fiber, depending on the specific model. At this stage, every mainframe element is brought together, including the suspension, the exhaust system, and other key components. This step is of the utmost importance, as it lays the groundwork for everything that comes afterward. The body is assembled by hand, using specialized tools and fixtures to ensure maximum precision and minimal gaps. Once the body and chassis are complete, the next step is the installation of the engine and the transmission. The engine is the heart of a Lamborghini, and putting it in place is an exceptionally intricate process. All Lamborghini engines are built and tested separately prior to being mounted in the car. Installing the engine also requires connecting it to the cooling system, the exhaust, and the vehicle's electronics. After this, the gearbox and the transmission system are fitted, allowing the engine's power to be transferred to the wheels. During this phase, all of the vehicle's critical systems are also fine-tuned, including the suspension and braking systems. The following stage involves installing the car's interior parts. This includes the seats, the instrument panels, the door trim, and the steering wheel. All these elements are made by hand using superior quality leather or Alcantara, in the case of sportier versions, along with other exclusive materials. Every piece is finished with meticulous attention to detail, creating a truly unique cabin. For instance, Lamborghini seats are crafted by hand to accommodate every curve of both driver and passenger, providing outstanding comfort. The steering wheel is also handmade and can feature a personalized design, according to the client's preferences. Once the principal interior components are set, the car moves on to the phase dedicated to connecting the electronic systems. Lamborghini cars are noted for their cutting-edge technology, so they come equipped with intricate infotainment setups, navigation, touchscreens, and safety systems. All wires and electronic parts must be hooked up with extreme accuracy to avoid errors or malfunctions. This process can take several hours and calls for highly qualified technicians who precisely follow each component's wiring diagrams. Having finished the physical assembly of the automobile, Lamborghini proceeds with the testing stage. Each vehicle goes through a detailed evaluation on special test stands, where every function and system is checked, ranging from the engine and transmission to the brakes and suspension. This helps detect any faults or issues before the car reaches the end buyer. One of the most vital segments of testing is assessing the car's performance dynamics on the track. Here, the automobile's characteristics at high speeds are evaluated, along with its maneuverability, braking force, and stability when cornering and accelerating. Once all tests have been completed, the car returns to the assembly hall for a final inspection. If all systems operate correctly, the vehicle undergoes one last quality assessment. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. Imagine this. Every year, more than 50 million drums are made around the world. But have you ever wondered how a piece of wood becomes a powerful instrument that sets the rhythm for music? From ancient shamanic rituals to modern rock arenas, drums have always been the heart of sound. To create the perfect drum, wood is dried for years, metal parts are crafted with jewelry-like precision, and membranes undergo special treatments. Today, we're going inside this process, step by step, from the lumber mill right onto the stage. The drum is one of the oldest musical instruments in the world. Its history stretches back at least 7,000 years, perhaps even more. The earliest drums were simple, animal skins stretched over wooden or clay bases. Over time, they evolved into the complex structures made from various materials that we see today. The oldest drums found by archaeologists date back to 5,000 years before Christ. They have been discovered in Africa, Mesopotamia, China, and Egypt. These early drums featured clay or wooden bodies with animal skin membranes stretched with ropes or glued on with resin. In shamanic rituals and religious ceremonies, drums were used to communicate with spirits. In ancient China and Egypt, drums coordinated armies on battlefields. In some African tribes, drums were even used to send messages over long distances. In the Middle Ages, drums became popular in Europe thanks to the Arabs, who brought them through Spain during the Muslim conquests. During this period, drums became integral to military music and later orchestras. A drum isn't just a chunk of wood or metal. Every part matters: the shell, the membrane, the hoops, bolts, and even the drumsticks. All these elements are crafted from carefully selected materials, and each affects how the instrument sounds. Wood used for drum shells must be properly dried, processed, assembled, and finished with lacquer. Metal parts are cast, polished, and protected against corrosion. The process is more complex than it first appears. Let's dive deeper into these details. Wooden drums have a special warmth to their sound. But as we said before, creating such a shell first requires carefully selecting, preparing, and drying the wood. The most popular choice for drum shells is maple. It produces a warm, balanced tone with excellent lows, mids, and highs, making it a staple in most studio and live drums. Birch provides a bright, aggressive sound, boosting the highs and lows, perfect for rock, metal, and live performances. Mahogany offers a deep, bass-rich sound with mellow highs, famously used in vintage drums from the 1950s and 1960s. Bobinga, a dense African hardwood, delivers a darker, powerful tone with great attack. More expensive, it's reserved for premium models. Oak, harder than maple, provides an exceptionally loud, penetrating sound ideal for live settings. Simply cutting down a tree and slicing it into boards is just the beginning. The tree must be harvested in a specific season, usually winter, when it contains the least moisture. Logs without cracks or knots are chosen. Freshly cut wood can have up to 60% moisture. First, the wood air dries outdoors for several months or even years. Then it undergoes kiln drying, reducing moisture content to between 8 and 12%. Next, boards are sliced into thin layers called plies, glued together under high pressure. The thickness of these wooden plies typically ranges from 0.024 inches to 0.118 inches. To produce uniform, thin layers without excess waste, several methods are used. Rotary cutting involves mounting logs onto special machines that spin them while blades peel thin, continuous wood strips, typically for budget drums. Bandsawing uses a flexible, continuous saw blade, moving in a loop to cut logs into thin plies. This method provides more precise cuts than rotary peeling, and preserves the wood grain better, although it creates more waste. For high-end drums showcasing exotic wood grains, manufacturers employ veneer slicing. Logs or boards are fixed, then moved against a sharp blade to shave off thin sheets. Laser cutting is the least common method. Premium drums sometimes feature solid wood shells, providing unique tonal qualities. But today, we're not focusing on those. Let us know in the comments if you'd like a separate video dedicated to that topic. First, the plies are coated with special glue, then stacked, forming a multi-layered structure. The number of layers typically varies from 4 to 20, depending on the desired shell thickness. Next, this stack is placed into specialized molds, bending the wood into a perfectly round cylinder. Even pressure is crucial to prevent defects and air bubbles in the glue. Afterward, the shells dry for several hours or even days. Once the glue hardens, shells are removed, edges trimmed, sanded, and drilled for hardware. This method is economical and allows manufacturers to experiment with combinations of wood types to influence sound characteristics. Polishing and applying finishing coatings is primarily manual work, especially for high-quality or custom drums. Shell surfaces are carefully sanded, removing all irregularities. Sanding happens either by hand or machine, progressing from coarse to extremely fine abrasives, usually from 120 to 400 grit. For glossy lacquer finishes, manufacturers may first apply primer to prevent excessive absorption by wood pores. Oil or wax finishes are rubbed in manually using soft cloths or brushes, penetrating deeply into the wood pores, protecting from moisture and enhancing the natural color. Lacquer is sprayed in several thin layers, drying completely between each coat. This process is performed by skilled artisans manually or by automated equipment in large factories. After drying, shells receive a final polishing to achieve the desired gloss, ranging from matte to mirror-like shine. In large companies like Pearl or Yamaha, producing hundreds of drums, lacquer is applied automatically. Still, final finishing always occurs by hand, since even the best machines cannot match human precision. Boutique manufacturers such as Cravioto, Brady, or Noble & Cooley finish every shell entirely by hand, making each drum unique and even more expensive. Even wooden drum shells have numerous metal parts: hoops, tension rods, and grommets. Hoops are typically chrome-plated steel, brass, aluminum, or even wood. Tension rods are commonly stainless steel or brass. Grommets are small metal inserts reinforcing the drilled holes in the shell. How are metal parts produced? Metal is melted at high temperatures, then cast or machined into required shapes. These parts are sanded and polished, removing roughness, then coated with protective layers like chrome or nickel to prevent rust. Historically, drums featured animal skins: cow, goat, or buffalo. Nowadays, synthetic plastics are more common due to their stability, durability, and weather resistance. Natural animal skin, being organic, expands and contracts with humidity and temperature changes. Moisture makes skins softer and sounds duller, whereas dry conditions cause them to shrink and crack. Synthetic materials maintain consistent tension regardless of weather. Once tuned, synthetic drumheads remain stable until manually adjusted. Drumhead materials, whether skins or plastic, are cut into circular pieces, treated chemically for flexibility, then pressed and stretched onto metal hoops. Preparing animal skins is truly spectacular. Inside large workshops, air smells of smoke, salt, and something sharp. Huge wooden vats line the walls, holding pieces of skin that visibly change color. This isn't mere soaking. It's true alchemy transforming tough, uneven hides into perfect drumheads. Initially, skins soak in large vats containing lime solutions, softening them and removing hair. After several hours or days, skins become lighter but still coarse. Next, they're treated with tanning substances, penetrating their structure on a molecular level. Vats emit steam. The aromas of wood, metal, and rawhide blend in the air. To avoid excessive stiffness, skins are stretched onto large wooden frames. Craftsmen stretch the skins manually, feeling thickness with their fingers. Sometimes steam is used, filling the workshop with thick vapor as skins are warmed before final treatment. Lastly, skins are rubbed with special mixtures: oils, waxes, sometimes herbal extracts. This keeps them flexible yet strong. In some regions, they're even smoked, imparting a light, smoky scent and improved water resistance. Even the best drum won't sound great without proper drumsticks. These are also crafted from carefully selected wood. Wood, typically hickory, maple, or oak, is sawn into blanks and air-dried naturally. But this takes time, so kilns usually speed the process, carefully controlling temperature and humidity, aiming for moisture content of 6 to 8%. Correct moisture levels are critical. Too moist, sticks warp. Too dry, they become brittle. Dried blanks are shaped on high-speed lathes. Each stick must have identical diameters. Otherwise, sticks within pairs produce different sounds. Simply turning a round stick isn't enough. Tip shape, taper in the middle, and weight distribution define how sticks sound when striking drums. High-speed lathes achieve precision within thousandths of an inch to ensure consistent quality. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called A.M. General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is half an inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose, wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent four-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time four-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Every single year, the world's oceans are left with hundreds of gigantic liners that used to be floating cities. Imagine this. Only one specialized shipyard in the country of India dismantles over 400 ships per year, and the utilization of just one cruise liner can yield up to about 44,000 short tons of steel. How does a vessel that once cost billions of dollars turn into a heap of scrap metal? Who makes money on this process? And why do the majority of ships finish their journey in southern Asia? Let us examine this process from the very first blueprint all the way to the very last cutting of the hull. Private yachts are produced all over the world, including in the United Kingdom, the Netherlands, Italy, and Turkey. But the major cruise liner production hubs are located in France, Germany, Italy, and Finland, where industry giants such as Chantier de l'Atlantique, Meyer Werft, and Fincantieri operate. Everything begins with the creation of a project, during which engineers and designers develop the overall structure, choose materials, and determine the technical specifications of the vessel. The design phase can last anywhere from 6 months to 5 years. Once it is approved, the shipyard begins manufacturing the main metal sections of the hull, which are later joined together in a massive dry dock or a specialized construction hangar. Construction starts with the production of large steel or aluminum sections that will form the hull. First, enormous sheets of metal are cut using laser or plasma cutting, and then they are joined by welding to create separate blocks. Each block can weigh anywhere from about 55 short tons to about 330 short tons, and their total number may reach into the hundreds, depending on the ship's size. After the welding is completed, the sections are painted with anti-corrosion coating and moved into a massive assembly dock, where the hull begins to take shape. The assembly process involves powerful cranes that lift the blocks and connect them to one another. Once the main structure is finished, the hull is reinforced with internal bulkheads, and initial communications are installed, including piping systems, ventilation ducts, and electrical cables. When the hull is fully assembled, it is launched into the water, and the fitting out of the interior begins. Partitions, electrical grids, heating and ventilation systems, air conditioning, and safety systems are put in place. At this stage, the ship gradually starts to look the way it will when it is completed. First, special soundproofing and thermal insulation materials are applied to the ship's metal hull, because the liner must be not only strong, but also comfortable. Next, metal frameworks are installed to serve as the foundation for the partitions and other structures. These frames are made of lightweight materials, such as aluminum or composite panels, to keep the vessel's overall weight lower. Thanks to modular technology, large sections of cabins and public areas are assembled at separate production facilities and then transported to the liner, where they are rapidly installed. Passenger cabins are usually manufactured as complete blocks, each including walls, flooring, plumbing, and furniture. These blocks are then transported to the ship and placed in their designated spots, after which they are connected to the ship's electrical network and water supply and ventilation systems. Larger liners can have more than 2,000 of these modules, and installing them can take several months. Public areas are much more complex, since each restaurant, theatre, or lobby has its own design and intricate architectural solutions. For example, theatre stages are equipped with moving platforms, sound systems, and lighting that is integrated into the ceiling. Swimming pools receive water purification systems, and sports courts are fitted with special non-slip surfaces designed to withstand wave movement. During the final stage, furniture, decorative panels, lighting, and finishing touches are installed. High-quality materials are used, ranging from exotic woods and marble to stained glass. Designers pay attention to every single detail in order to create an atmosphere of luxury and comfort. Once construction is complete, all systems undergo meticulous testing, including elevators, ventilation, safety features, and communication lines, so that the liner is fully prepared to welcome passengers. At the same time, powerful engines and control systems are installed on board. The main engines, which are typically diesel or hybrid, are mounted in the engine room before the liner's hull is completely enclosed. Each engine can weigh anywhere from about 22 short tons to about 55 short tons, and there may be between 3 and 6 engines depending on the ship's size. They are delivered to the shipyard dock by specialized cranes, then lowered through the engine room's top hatch and attached to vibration damping mounts that reduce noise and vibration during operation. After the engines have been installed, drive shafts are added to transmit rotational motion to the propellers, or, in the case of electric motors, they are connected to the power supply system. Most modern liners use azipod units, which are powerful electric motors capable of rotating around their own axis, giving the ship excellent maneuverability. All power units are connected to control systems located on the bridge and in the engine room. Once every technical system is in place, the liner is readied for its initial tests. First, static tests are conducted while the ship is still in the dock, checking how the engines function without leaving port. The power units are started up, and the electrical supply, fuel pumps, cooling systems, and emergency mechanisms are tested. Computerized control systems, which manage navigation, automatic speed adjustment, and ship stability, are also checked at this stage. Following these static tests, the liner is launched for sea trials, which last from about 2 weeks to about 6 weeks and include checking speed, maneuverability, and the operation of all systems under real-world conditions. The captain and technical personnel test how the vessel responds to commands, examining braking efficiency and the performance of the stabilization systems. The liner is taken into open waters, where the engines are tested at maximum power. Fuel consumption is measured, and noise and vibration levels in cabins and public areas are evaluated. In the final phase of testing, safety systems are examined by simulating emergency scenarios, testing firefighting systems, lifeboats, evacuation routes, and communication with shore-based services. Only after all tests are successfully completed is the liner formally handed over to the client, and it sets sail on its maiden voyage. But sooner or later, every liner heads out on its last voyage. Since no technology lasts forever, what happens to yachts and other vessels afterward? Are they actually utilized? And if so, how? According to data from the International Maritime Organization, around 1,000 seagoing vessels are utilized each year, of which about 200 are large cruise liners and passenger ships. Most of these vessels are dismantled in South Asian countries such as India, Bangladesh, and Pakistan, where the world's largest ship utilization shipyards are located. For instance, in the city of Alang in India, there is one of the biggest shipyards, which processes over 400 ships per year. First, the ship's owner assesses the condition of the liner and compiles a list of materials that can be recycled, sold, or require specialized disposal. The utilization of a single large cruise liner can produce up to about 44,000 short tons of steel, which after recycling is used in construction and other industries. In addition to metals, other materials such as wood, glass, and plastic are removed from the vessels for recycling or safe disposal. During this period, the ship heads to the specialized shipyard that handles the disassembly of ships. The largest of these facilities are located in India, Bangladesh, Turkey, and Pakistan. The liner or yacht makes its way to the site for utilization under its own power, or is towed if its engines are no longer functional. When the vessel arrives at the shipyard, the preparatory work begins. A team of engineers and environmental specialists evaluates the potential risks connected to hazardous substances, including fuel, lubricants, coolants, chemicals, asbestos, and lead. All of these materials must be carefully removed to prevent environmental contamination and to protect the workers' safety. In the first step, any remaining diesel fuel is pumped out of the tanks, which can amount to anywhere between about 10 short tons and about 55 short tons, depending on the size of the vessel. Next, the pipelines, oil filters, and engine cooling systems are cleaned to remove all residual lubricants and chemicals. Specialists also deal with air conditioning and firefighting systems, which might contain harmful gases like freon. After that, the ship is disconnected from all power. The electrical networks are shut down, and the batteries containing toxic substances are removed. In the engine room, the generators are dismantled. They can be resold or used on other ships. During this period, specialists also check for hazardous materials, such as asbestos, which was once used for pipe and wall insulation. Asbestos is carefully taken out, sealed, and delivered to specialized facilities for safe disposal. The next step involves removing all equipment and items that might be reused or sold. Furniture, lighting fixtures, plumbing, doors, decorative panels, carpets, and even kitchen appliances are dismantled from the liner. Many of these items are sold on the secondary market or used on other vessels and in hotels. The following stage is dismantling. First, the ship is secured in a dry dock or pulled onto a specially designated beach, which is common in South Asian countries such as India or Bangladesh. This stabilization is necessary to keep the hull steady during cutting because losing balance could cause an accident. Next, the upper structures are gradually taken apart, including the top decks, bridge, funnels, and other external components. These sections are typically removed in large pieces using cranes. Workers start dismantling the upper structures and decks, steadily moving down toward the main hull. Metal parts like steel and aluminum are cut into smaller segments, and the separated materials are sorted and prepared for subsequent recycling. For example, steel is melted down to create new products, while non-ferrous metals such as copper and aluminum are put to use in various industries. When the upper structures have been fully removed, the main hull is cut apart. Several methods can be used, depending on the thickness of the steel and where the ship is located. The most widespread method is gas cutting, where specialized torches heat the metal to over 1,500 degrees Celsius, which is about 2,732 degrees Fahrenheit, and then the steel is sliced by a stream of oxygen. For thicker steel sections, which can be up to about 8 inches thick, plasma cutting or hydraulic shears may be used. Cutting of the hull begins from the top and proceeds downward so that the structure does not collapse under its own weight. Huge steel blocks, weighing anywhere from about 55 short tons to about 110 short tons, are separated and moved to specialized areas, where they are further broken down for recycling. On average, the hull of one large cruise liner can yield from about 33,000 short tons to about 44,000 short tons of steel, which is later reused in construction and shipbuilding. Special attention is paid to cutting the underwater part of the hull, since it is the sturdiest section and contains ballast tanks that might hold residual water. Underwater welding and cutting techniques are employed if part of the hull remains in the water at that stage. In the final phase of dismantling, the last remains of the keel and bottom are cut into fragments, which are loaded onto trucks or barges for transport to metallurgical plants. Utilization of cruise liners and yachts can last from a few months to more than 1 year, depending on the vessel's size and construction. Completing the dismantling process signifies that the ship officially ceases to exist. All materials suitable for reuse are sent for recycling, and everything else that cannot be repurposed is disposed of in accordance with environmental regulations. It is important to note that the utilization process must meet international environmental standards. Organizations such as the International Maritime Organization develop guidelines and standards for the environmentally sound utilization of ships, known as the Hong Kong International Convention for the Safe and Environmentally Sound Recycling of Ships. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types. Lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection, a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund. often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 0.1 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/1600 to 4/10 of an inch, are suitable for sturdier products like structural elements or, in some cases, new aluminum cans when further processing requires that specific diameter. Thick wire rods, over 4/10 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 4/100 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end to end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement, or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. Did you know that over 2 billion cups of coffee are consumed every single day around the world? But how does your morning drink begin its journey from a tiny coffee cherry? Today, we're uncovering the secrets of instant coffee. From the first blossoms of coffee trees to the cutting-edge factories where beans transform into aromatic powder. Why is Arabica so delicate and Robusta so hardy? And how does production involve technologies that seem straight out of a sci-fi lab? Stick around. You'll be amazed by how many hands and minds it takes to create every jar of coffee. Before beans make it to the factory, they travel a long way. From small coffee plantations to industrial mills. And this journey starts long before the beans are ready to work. First, let's talk about Robusta and Arabica. They're like totally different personalities. They grow in different conditions, offer distinct flavors, and have unique growing demands. Fun fact: instant coffee usually uses Robusta, a bean known for its strength and high caffeine content. Arabica is also used, but less frequently, mainly in premium blends to add a smooth, sweeter flavor. Arabica is the premium bean. It's grown high up in the mountains, typically at elevations of 800 to 2,000 feet above sea level. It's picky. It loves mild climates, consistent rainfall, and temperatures between 60 and 75 degrees Fahrenheit. Robusta is less fussy. It thrives in lowlands, can handle heat, humidity, and even pests. Its ideal growing temperature can reach up to 86 degrees Fahrenheit. It's often cultivated in tough climates where Arabica wouldn't survive. Coffee plantations look like small forests. Coffee trees are grown from seeds, and get this, they take up to 3 years to bear their first fruit. Yep, 3 years before those cherries, which aren't even the coffee beans yet, but their outer shells appear. The trees are planted on specially prepared terraces, especially Arabica on slopes. The soil needs to be loose, rich in minerals, and moisture balanced. On many plantations, work is still done by hand, though some larger farms now use machines for planting. Coffee cherries take about 9 months to ripen after the trees bloom. And here's where the magic begins, timing the harvest just right. Handpicking is the best and most precise method. Workers pick only the ripe cherries, leaving the green ones to mature. It's labor-intensive, but guarantees quality, especially for Arabica. Robusta is often harvested with machines that comb cherries off the trees. It's faster and cheaper, but ripe and unripe cherries end up mixed. Handpicking Arabica ensures better quality, but requires a massive workforce. Entire villages or even seasonal workers from nearby regions often help on large plantations. Harvested cherries aren't beans yet, they're just the shells. To extract the coffee beans, cherries undergo processing. There are two main methods: wet processing and dry processing. Wet processing is mostly used for Arabica. Cherries are soaked in water, where the pulp dissolves and the beans separate. It's pricier, but results in a clean, delicate flavor. Dry processing is more common for Robusta. Cherries are simply spread out to dry under the sun, and then the shells are removed. It's cheaper, but creates a bolder, more intense taste. After processing, the beans are sorted by size, weight, and quality. The best beans go into premium coffee products, while smaller or slightly damaged ones are used for more budget-friendly options or instant coffee. Here's something cool I learned. Robusta beans are usually round and tougher, while Arabica beans are oval and a bit softer to the touch. Once beans are ready, they're packed in classic jute bags. Why jute? It lets the beans breathe during transportation. On plantations, these bags are often loaded onto small trucks or even motorcycles to reach nearby ports or warehouses. Then, the beans are shipped in large containers that can carry hundreds of tons of coffee at a time. Beans often pass through several countries before reaching the factory. For example, coffee might be grown in Vietnam, one of the world's largest Robusta producers, processed in another country, and roasted or turned into instant coffee at a factory in Europe or the US. Before beans are transformed into instant coffee, they're checked for quality multiple times. On plantations, defective cherries are removed before processing. Before shipping, beans undergo another round of checks at warehouses and ports. This includes examining size, color, and aroma. At the factory, samples from each batch are tasted to ensure the flavor meets standards. Everything starts with coffee beans. At the factory I visited, roasted beans are delivered, and their smell, wow! It's that rich aroma you get when you walk into a coffee shop. Fun fact, roasting follows an incredibly precise schedule. Every second impacts the final flavor. So, where does roasting happen? At roasting facilities. Roasting is a whole universe of its own. It significantly affects coffee's taste and aroma, so it's taken seriously. There are several ways this can go down. Sometimes, especially for large Robusta volumes, beans are roasted in their country of origin, like Vietnam or Brazil. These countries have massive export-focused factories, which cut down on logistics costs. Big brands have their own roasting facilities in key regions. For example, in Europe or the US, there are giant factories specializing exclusively in roasting. Roasting beans separately isn't just a preference, it's logical. Green coffee beans are easier to transport long distances because they're less sensitive to storage conditions. Specialized facilities ensure a consistent roast level needed for specific products. Plus, depending on the end use, instant coffee or ground coffee, beans are roasted differently. Roasting coffee is a science. Beans are heated in rotating drums at temperatures around 400 degrees Fahrenheit. The roast time depends on the desired profile, lighter for softer flavors, darker for bold, intense notes. Instant coffee typically uses dark roasts. This enhances aroma and adds a bitterness that holds up even after processing. Roasted beans are cooled and packed to preserve their aroma. The factory receives this semi-finished product and focuses on its processes. It's a bit like a chef starting with a ready-made base to create a masterpiece. The first step after delivery is grinding the beans to a dust-like consistency. No, this isn't your regular grind for a French press or espresso. Industrial mills turn beans into particles finer than sand grains. Why so fine? I asked one of the staff. The answer was simple. The smaller the particles, the more efficiently the flavor and aroma are extracted in the next steps. Here's where the real chemistry begins. The ground powder goes into special extraction chambers, where it's brewed with hot water under pressure. Think of it as a giant coffee maker. This is where all the flavor and aroma you enjoy in your instant coffee are drawn out. What surprised me? The water temperature is controlled to the exact degree to avoid overbrewing. If it's too hot, the taste becomes bitter. Too cool, and the coffee loses its richness. The extract from these chambers undergoes multi-stage filtration. All unwanted particles are removed, leaving only a liquid concentrate. This concentrate looks like thick syrup and has such a strong aroma, it'll make your head spin. Next comes the most fascinating part. The liquid concentrate is turned into powder or granules using two main methods: spray drying or freeze drying. Spray drying involves blasting hot air to dry droplets of concentrate, leaving behind dry powder. It's fast and relatively cheap, but sometimes loses some aroma. Freeze drying is more complex. The concentrate is first frozen to extremely low temperatures, then sublimated, turning ice into vapor and leaving dry granules behind. It's pricier, but preserves maximum flavor. At the factory I visited, both methods were used depending on the coffee type. For premium lines, only freeze drying was used. The finished powder or granules are packed into jars, sachets, or sticks. It's all automated. Machines measure exact amounts, seal the packages, and add protective valves to preserve aroma. By the way, these valves are a real technological breakthrough. They let air out of the jar, but don't let it back in. You might wonder, how do they keep the aroma? The secret is that some of the coffee oils and aromatic compounds lost during extraction are collected separately and added back to the final product. It's like a little bonus that makes instant coffee so familiar and fragrant. Is instant coffee real coffee? You know, I was a bit skeptical myself until I saw the whole process. It really is 100% coffee, just with a touch of engineering magic. Actually, scratch that, it's more like technical mastery. The difference between instant coffee and freshly brewed coffee is like the difference between homemade pizza and takeout pizza. They're both great, but in different ways. Instant coffee is quicker, more convenient, and still incredibly flavorful when done right. After the tour, I was blown away by how intricate and well thought out the process is. And you know what amazed me the most? The sheer number of people involved, from engineers monitoring the equipment to tasters checking every batch. Yes, tasters. Turns out it's a real profession. Imagine having a job where you drink coffee and evaluate its taste. Isn't that the dream? Instant coffee isn't just powder in a jar. It's a monumental effort, cutting-edge technology, and a love for a drink that brings us comfort, even on the busiest days. So, next time you make yourself a cup, remember the many hands that work to deliver that aroma to you.